Welcome back everyone. In the last lecture, we had seen the problem that occurs when repeated eigenvalues are there for the state matrix. If we can find out linearly independent eigenvectors for the state matrix corresponding to each of the eigenvalues even when they are repeated, then we could diagonalize the matrix. However, there may be cases when we won't be able to find out linearly independent eigenvectors corresponding to each of the eigenvalues when the eigenvalues are repeated. How do we solve that problem? Basically, the question is, if I cannot diagonalize the state matrix, is there a way of going to some other form and finding out the matrix exponential e to the power of at easily? If you remember, in this example we had the issue that the eigenvector corresponding to the eigenvalue 1 was scaled version of this 1 0 0 vector. Okay. Although 1 is repeated 2 times, we only got one vector which we could take as linearly independent, and corresponding to lambda 1 equal to 2, we could easily find out one vector which was 5 3 1 in this case. So, if you remember that we had a deficit here when we were trying to find out the T matrix, if we construct the matrix, then we had a deficit of one vector. Okay. So, the question is, or what should we replace deficit vector with so that we get to some nice form if not diagonal. Okay. This brings us to the idea of generalized eigenvectors. Now, what is generalized eigenvectors? First of all, let us recall the definition of an eigenvector. So, if P is a square matrix, then lambda is an eigenvalue of P if there exists a non-zero vector V1 such that P of V1 equal to lambda of V1. Okay? Or in other words, V1 must satisfy this equation. Then we call V1 to be an eigenvector of P corresponding to the eigenvalue lambda. If you remember, I had emphasized the fact that you will not get unique eigenvectors corresponding to an eigenvalue. If V1 is an eigenvector, then alpha of V1 will also be an eigenvector. So, you can come up with infinitely many eigenvectors for a particular eigenvalue. Now, what is a generalized eigenvector? So, a non-zero vector Vi plus 1 is called a generalized eigenvector of rank I if P of Vi plus 1 equal to lambda of Vi plus 1 plus Vi, where I is from 1, 2 and so on. So, suppose I want rank 2 generalized eigenvectors. So, rank 2 generalized eigenvector will satisfy this equation, P of V2 is equal to lambda of V2 plus Vi, where Vi is an eigenvector. Remember, this is an eigenvector here, not a generalized eigenvector, but an eigenvector that satisfies this equation. Okay. If you have such an equation, then we will call V2 to be a rank 2 generalized eigenvectors. Remember, this is not the rank of a matrix. Okay. This is just a name, okay, generalized eigenvector of rank 2. Okay. The same equation can be rewritten in this form. If I take this lambda of V2 term to the left, I can rewrite this same equation in this form, and notice that if I multiply both sides by P minus lambda I again, I get P minus lambda I whole square V2 equal to P minus lambda I V1. But the right hand side here is 0, right, because V1 is an eigenvector. So, I can rewrite that as P minus lambda I whole square V2 is equal to 0. So, this means that V2 must satisfy this equation. Okay. So, remember, P minus lambda I whole square V2 equal to 0. So, V2 must satisfy this equation. Here is something to think about. Does P2 satisfy this equation? Okay. Suppose P2 satisfied this equation, then P of V2 must be equal to lambda of V2, right. Then V2 would become an eigenvector, right. But we know that V2 is not an eigenvector. So, this equation should not be satisfied by V2. Okay. if I go to rank 3 generalized eigenvector, so then rank 3 generalized eigenvector must satisfy this equation. Again notice here V2 here is a rank 2 generalized eigenvector. Okay. So, what does this mean? I can keep on going up now. You can see that if I multiply both side by p minus lambda I now, I get this. Now, the right hand side is not 0, right. I have just now told from here itself. I can write the right hand side as, this right hand side can be written as V1, okay, because this is the definition. But again if I multiply both side by p minus lambda I, again I will get this, but the right hand side here will become 0. So, I get this. So, again you can see that V3 or a rank 3 generalized eigenvector is a solution of p minus lambda I whole cube V3 equal to 0. But does it satisfy p minus lambda I whole square V3 equal to 0? No. Does it satisfy P1 this V3 equal to 0? No, this does not satisfy, because if it satisfied this, then V3 is an eigenvector of the matrix. So, you can see what is going on here. Okay. Let me go one more step up. So, if I go to a rank 4 eigenvector, then generalized eigenvector. So, rank 4 generalized eigenvector will satisfy this equation where V3 is a rank 3 generalized eigenvector. Again, what was a rank 3 generalized eigenvector? They satisfy this equation where V2 is a rank 2 generalized eigenvector. Okay, and a rank 2 generalized eigenvector satisfy this equation where V1 is a rank 1 generalized eigenvector, or in other words it is an eigenvector. So, a rank 1 generalized eigenvector is nothing but an eigenvector. See, V4 must satisfy this equation, right, but it cannot satisfy these 3 equations. Okay. Here P of minus lambda I whole cube V3 was 0, but it did not satisfy these 2 equations. Similarly, in this case P of lambda I whole square V2 equal to 0, but it did not satisfy this equation. So, a non-zero vector Vi plus 1 is called a generalized eigenvector of rank I if it satisfies p minus lambda I whole to the power of I Vi equal to 0, and it does not satisfy this equation. Okay. So, then we say that this is a generalized eigenvector. Now, how does this help us? You see, for this example that we took, I can take this A matrix, and again you remember that for lambda 1 equal to 1, which is an eigenvalue of this, I could easily find out the eigenvector. So, this is the eigenvector, this is an eigenvector corresponding to 1. Okay. As a matter of fact, any linear combination of this 1 0 0 vector. Now, let us try to find out a generalized eigenvector. So, if you go for a minus I whole square V2 equal to 0 and a minus I V2 is not equal to 0, I have to find something like this, right. So, a minus I whole square comes out to be this matrix. Now, notice one thing, that this vector which was an eigenvalue will always satisfy this equation. Why? Because you see, if a minus I whole square V1, so I can rewrite this as a minus I whole into a minus I V1. But this is 0, right, because V1 has an eigenvector. So, therefore, this expression will also come out to be 0. So, which means that the eigenvector that we found out will satisfy this equation, remember that. Okay. So, that means 1 0 0 beta 1 will be a solution, S1 here will be a solution of this. But is this the only solution? No, there are more things that you can find. Okay. As a matter of fact, the solution for this equation will look something like this. You can take the solution set here, and then it can have other elements of the form 0 1 0 beta 2, and the summation of this will also be a solution. You can have a look at it, and you will see that this will work. So, this will be a solution set for this. Okay. Now, a easy way of, instead of writing this solution every time, an easy way of writing this is, so what is this? This is nothing but I can consider this to be the generator of the set. I can use this to create all the solutions for this equation, right. So, we can say that span of 1 0 0 is a solution of S1. So, the word span means the linear combination of this vector. Now that since here we have only one vector, so basically the scaling of this vector or span of a set say V1, V2 means all the vectors which are formed by linear combination of these two vectors. Okay. You can take two vectors and then you can keep on taking linear combinations, you will get new vectors, right. Collect all the vectors, you will get a big set, and that set is called span of V1 and V2. V1 and V2 are acting as generators for this set in this case. Okay. So, in this case 100's linear combination means alpha times or beta 1 times of 100, so that generates the entire set. Here you can see that I can take these two as the generators, because if I take only this, I am not taking into consideration solutions of the form, these type of solutions I am not taking into consideration if I take only this. Okay. So, in this case these two vectors, okay, I can use as generators, again they are generating this entire solution set. So, these two will be the generators and we call it to be span of these two, which means that the linear combination of these two vectors is the solution set. So, it is a short way of writing the entire thing. Let us look at this problem that we were dealing with, and let us try to see how can we find out the modal matrix that will bring it to a nicer form. What is a nicer form? We will look into that now. Okay. So, when we found out eigenvectors, this was the solution set that we got, right. So, let me say that this is the set of eigenvectors. Okay. This is the set of eigenvectors. So, let me call this eigenvectors. And how was it formed? It was formed by A minus lambda I V equal to 0. The solution set of this gave me the eigenvectors. Now, since I could only find one linearly independent eigenvector here, which was 100, because all the rest are beta times of 100 only, I could only find one linearly independent eigenvector here. So, I am stuck with only one vector, I need another, right. So, how do I find out another? So, I go to the generalized eigenvectors set. Okay. The generalized eigenvectors of rank 2 are the sets which will satisfy this, but will not satisfy this equation, right. They should not satisfy this equation. Question that I can ask is, which are the vectors that satisfies this equation? The eigenvectors will satisfy this equation, we know, they have to satisfy this equation. Now, what are the other vectors that can satisfy this equation? There will be another set. Okay. So, this entire set here will satisfy this equation, correct, and this entire set will include the eigenvectors also. Now, what are rank 2 generalized eigenvectors? Rank 2 generalized eigenvectors are those vectors which satisfies this equation, but does not satisfy this equation. That means, they are not eigenvectors, right, which means that this part of the set, this green part of the set here, the green part of the set here are your generalized eigenvectors of rank 2. I hope you understand this. Okay. Although, see, remember, this equation is satisfied by both eigenvectors and the rank 2 generalized eigenvectors, but the rank 2 generalized eigenvectors do not satisfy A minus lambda I V equal to 0. So, which means this green part becomes your rank 2 generalized eigenvectors, because they cannot satisfy A minus lambda I V equal to 0. Now, the idea is this. Now, we will construct the matrix. Now, how do we construct the matrix? So, you start off with a vector from this set. Okay, you start off with a vector from this set. Okay. In this example, we have only one vector in that, like one vector as in that set can be generated by this vector, right, because I know that 0 1 0 beta 2 does not belong to and is not an eigenvector of A, right. So, I will consider that to be V2. Okay. Now, what is V2? V2 is the matrix. We will form the matrix V1, V2, V3, where V1 is the first column, V2 is the second column, V3 is the third column, say. So, the second column I am choosing as V2. What is the third column? The third column will be eigenvector corresponding to eigenvector corresponding to 2, because for 2 we could easily find out an eigenvector, right, since it was only one times appearing as an eigenvalue. So, I just needed one eigenvector and I could easily find that out. So, V3 will be that eigenvector. Only problem was that I could find out V1, which is an eigenvector corresponding to 1, but I could not find out the second column. So, what I am doing is that I am choosing the second column here to be this generalized eigenvector, which is 0 1 0. Now, what I will do is I will multiply this 0 1 0 with a minus lambda I, lambda being 1 in this case, to get a new vector which is 1 0 0. It turns out it came out to be this, it might not come out to be this, it can be something else also. Now, one thing to notice here is that as soon as I do that, what happens? See, when I find out a minus I V2, okay, I get a new vector, right, but I know that this vector will be eigenvector, right, because a minus lambda I V2 satisfies this equation, right. So, in this case, so when I multiply a minus I into V2, I will get a eigenvector here. So, that is what is happening here. When you do a minus I V2, you get an eigenvector 0 1 0 0, and I will use that as my V1. Okay, and V3 I had already found out to be 5 3 1. So, you can see what I have done basically. So, first, okay, let's step back and try to understand what we are doing again. First, we took the matrix, we found out the eigenvalues of the matrix. For the eigenvalues which are distinct, we can easily find out eigenvectors. So, that is not a problem, and these eigenvectors will be linearly independent of each other. That is also not a problem, because they are distinct. These eigenvectors corresponds to distinct eigenvalues or different eigenvalues. So, they will be linearly independent. The problem comes when there is a repeated eigenvalue. Now, corresponding to a repeated eigenvalue, the repeated eigenvalue might have appeared, say suppose 2 times. In this example, the repeated eigenvalue appeared 2 times, right. The multiplicity of the eigenvalue is 2. This is also called algebraic multiplicity of the eigenvalue. Algebraic multiplicity of an eigenvalue is the number of times the eigenvalue has appeared as an root of determinant of a minus lambda I. Okay. So, the algebraic multiplicity of the eigenvalue is 2 in our example. If I have to diagonalize the matrix, I need for each of these eigenvalues one eigenvector, such eigenvectors that both these eigenvectors are linearly independent to each other. Turns out that in this example we were not able to find such a set of eigenvectors. In one of the examples in the previous lecture, we could do that. Okay, if you go back and check, you will see that we could find out eigenvectors in that example, and that is why we could diagonalize the matrix. But since in this case I cannot find out such an eigenvector, I will not be able to diagonalize the matrix. However, we will be going to something called a Jordan form, okay, which is somewhat nearer to a diagonal matrix, and it also will help us to find out the matrix exponential. Now, the question is, how do I get to that form? To get to that form, the idea is simple. First, you see, you wanted 2 eigenvectors. Since you are not getting 2 linearly independent eigenvectors, you first find out the rank 2 generalized eigenvector. Okay. So, once you find out the rank 2 generalized eigenvector, take that rank 2 generalized eigenvector as your second column of this matrix. Then multiply that eigenvector with a minus lambda I, lambda being 1 in our example. So, a minus I into that V2 will give you a new vector, right. It turns out that this vector has to be an eigenvector, because it will satisfy the relation, right, a of V2 equal to lambda of V2 plus V1. This new vector that you get is your first column of the matrix, and that is what we are going to do here. You can see that I took this as the seed. In this case, I used this, okay, and then I multiplied this vector with a minus I. I multiply this vector with a minus I to get to a vector here, okay. And for this case, for this eigenvalue, 2 eigenvalue, it was straightforward, it is only repeated once. So, I needed 1 eigenvector that I could easily find out. Now, I will form the T matrix, and the T matrix will be 1 0 0, 0 1 0 and 5 3 1. And you can see that now if I do T inverse of 80, it will come out to be 1 0 0, 1 1 0, 0 0 0 2. Why is that so? Why will this be true? You can easily see this, right. See what we are trying to find out, we are trying to find out T inverse of 80. Suppose T inverse of 80 is some A bar, which is nothing but A of T is equal to T of A bar. I am trying to prove why you will get this, okay. I mean I am just trying to give you it, you will always get this, but why will you get this is because you have carefully chosen the columns of the T matrix. Now what is this equation like? So this equation is like A times V1, V2 and V3, right, is equal to V1, V2, V3. These are your columns, and here we will have your A bar matrix. Now look at this. What is the first? So what will be the first column on the left hand side? The first column will be A of V1, right. And what is A of V1? I know that A of V1 is an eigenvector, right, because I found I got to V1 by multiplying V2 by A minus I. So V1 is an eigenvector, so that means it must satisfy this, where lambda 1 is 1 in this case. So it must satisfy this, which means that the first column here should be 1 0 0. What is the second column on the left hand side? A V2. But what is A V2? I know that A V2 is equal to lambda V2, lambda being 1 here, plus V1, right, because I know that A minus, why is this true? Because I know that by construction, the way I have constructed V1, it followed this equation. So therefore this must be followed. Now if this must be followed, then the equation here would come out to be 1 1 0, the column here. And finally what is A of V3? A of V3 is equal to lambda 3 of V3, where lambda 3 is 2 in this case. So in this case this must come out to be 0 0 2, and you can see this is exactly the matrix that we found out, okay. So this will work. I mean I just showed you this so to verify that yes it works, okay. Only thing is that you have to maintain the order. So remember the generalized eigenvector is here, and then we are moving like this. If there were more, we will move like this, okay. If you change the order, you can check what it will look like. So suppose you take the generalized eigenvector first and then the eigenvector, then actually the matrix will look like something like this. You can try this on your own, okay. In that case T inverse of 80 will look something like this. You can even change the order here also. You can take this to the beginning. If you take that to the beginning, then since 5 3 1 is coming at the beginning, so the matrix will look something like this. T inverse of 80 matrix will look something like this. This should have been 1. Yeah, this T inverse 80 will look something like this. So you can go ahead and keep on playing around with this, so that you understand that how does this form looks like. Now this matrix is what is known as a Jordan canonical form. Okay. So what was the diagonal form? The diagonal form was 1 1 2, but since we could not diagonalize it, okay, so we will go to the best case possible. So corresponding to 1, since we had repeated eigenvalue and we could not find out enough number of eigenvectors, so that the block will look something like this. So it will be an upper triangular block of this form, and this is called a 2 cross 2 Jordan block, corresponding to, this is a 2 cross 2 Jordan block corresponding to lambda equal to 1. For each eigenvalue you will get a Jordan block. For example, in this case you got a Jordan block, but this is just a 1 cross 1 Jordan block. So it is the diagonal entry itself, okay. So these are called Jordan blocks, and the size of the Jordan block will depend upon the generalized eigenvectors that you are getting, okay. Now how does this help us? Okay, I will take another example later, but first let us see the problem that we started with. So how will this help us? Now remember, if your matrix is in diagonal form, if P is in this form, if you remember, e to the power of Pt will be this, simply e to the power of lambda 1 t, e to the power of lambda 1 t here, and it is very simple to write, right. Now what about this case? Since it is not diagonalizable, so suppose T inverse of 80 came out to be this form. Again you can see in this is a Jordan form. Okay. Why is it a Jordan form? Corresponding to lambda 1 you have a 4 cos 4 Jordan block. What is a Jordan block? Again it is an upper triangular, in some cases lower also, but let us consider upper triangular. So it is an upper triangular matrix where the diagonal entries are the eigenvalues are the same eigenvalues, and the super diagonal entries are 1 here. Okay. Now corresponding to lambda 2 there is no Jordan block, corresponding to lambda 3 there is no Jordan block. So in this case, now if I try to find out e to the power of pt, in this case it was quite easy. In this case also it turns out that it will be of this form. So basically corresponding to this 4 cross 4 block you will get a 4 cross 4 block here, and this block you see the diagonal entries are similar to that for the diagonal case, but here there will be t e to the power lambda 1 t, t square by factorial 2 e to the power lambda 1 t, t cube by factorial 3 e to the power lambda 1 t, and so on. If I take another example, here you can see that now you have a 2 cross 2 Jordan block. Again corresponding to lambda 1 you have another 2 cross 2 Jordan block here. Okay. So corresponding to the same eigenvalue you can have different Jordan blocks, but within a Jordan block it cannot be different eigenvalues. So here this is again a 2 cross 2 Jordan block. So we have two cross 2 Jordan blocks here. We have lambda 2 which is a 1 cross 1 block, and then we have lambda 3 which is a 1 cross 1 block. So now if you want to find out the e to the power of pt, again directly you can again write it in this form. So for corresponding to each of the blocks in the diagonal, this is one block in the diagonal, this is one block in the diagonal, this is one block, and this is one block. So this is a block diagonal matrix therefore. Okay. So corresponding to this block the exponent will look something like this, corresponding to this block it will look something like this, and so on. Okay. Question is, why is this true? Okay. Let us look for the diagonal case. For the diagonal case you see it is quite straightforward for the diagonal case, because if p is in this form, you see e to the power of pt has this, can be written down in this infinite series. Okay. Now in this infinite series it is like I plus pt plus p square t square by 2 plus p cube t cube by 3 and so on. Okay. Here what is I? I is a identity matrix, p is this matrix multiplied by t, p square is again the diagonal terms get squared multiplied by t square by 2 and so on. Now if you add these up, this is what you will get. Okay. If you add these up, the diagonal entries will become something like this, and what is the diagonal entry here? This is nothing but e to the power of lambda 1 t, right. So I can go ahead and replace this. That is the reason that when you take p to be this matrix, a diagonal matrix, e to the power of pt just the diagonal entries becoming e to the power of lambda 1 t, lambda 2 2e and so on. The same thing we can do for the Jordan case, and let us look at that for the Jordan case now. For the Jordan case the p matrix looks something like this. Now we will do the same thing that we did for the diagonal case. Let us go ahead and write it down. So I matrix is this identity matrix, pt becomes this, p square will take this form. You can go ahead and multiply and check what p square becomes. This p square will look like this, p cube will look like this, and then t cube by factorial 3 and so on. Now if you add up these points, you can see what will be the 1 1 element. If you add up the 1 1 elements, the 1 1 elements will come out to be this term, this term, this term, this term. Okay, all these terms taken together, but what is this? So this is nothing but e to the power of lambda 1 t. Okay. So the diagonal elements will come out to be 1 e to the power of lambda 1 t. In this case this element will again come out to be e to the power of lambda 1 t, and similarly this one also e to the power of lambda 1 t. You can check that the diagonal elements are similar to the diagonal case. Now let us come to the 1 2 element. Let us look at the 1 2 element here. Okay. So how will the 1 2 element look like? So the 1 2 element here will look something like this. You will add 1 into t. So t, then 2 lambda 1 into t square by 2. So this is what it will be. Then 3 lambda 1 square t cube by 3. So this is what it will be. So you can add these things up. From here you can see from this 2 and this is factorial 2, I can cancel out. I will get lambda 1 t square. From here I will get lambda 1. So this will become lambda 1 square t cube by factorial 2, right. Similarly it will go ahead, I can take t common from here, and if I take t common, the inside term here becomes e to the power of lambda 1 t. So, that means the 1 2 term, the 1 2 term here, the 2 2 terms, all these things will become t e to the power of lambda 1 t for the red part. Okay. What is the 1 3 term? The 1 3 term starts from this point. So, again 1 into t square by 2, okay, then 2 lambda 1 t cube by factorial 3 and so on, and that again from here if I take t square by factorial 2 common, t square by factorial 2 e to the power of lambda 1 t. Okay, and that is the reason you see this is what the matrix looks like. Okay, there is a nice structure to it, you do not even have to calculate. Once the matrix goes to the Jordan form, you can easily go ahead and write this down. Okay. Now, if I take an example where we are actually trying to find out the solution of a state equation, suppose this was the matrix that we had, this is the A matrix that we are dealing with. Okay. So, for this A matrix, suppose the initial condition is this, I have to find out x of t. Okay. Now, we already know what the model matrix would be, the model matrix will be this, then we define a transformation of this form, because we know that once we define a transformation of this form, then what will happen if I define z. So, this is z of t is equal to m inverse of x, we have done this actually in the last class itself. So, this is x dot equal to a x plus b u, and then here x is being replaced by m z. So, this becomes m of z dot is equal to a of m of z plus b of u, which means that z dot will become equal to m inverse of a m z plus b plus m inverse of b u, but we know that m inverse of a m is nothing but a Jordan matrix of the form 1 1 0 1 0 0 2 0 0, just now we found it out, right. Okay. So, that is the idea. So, once we do this transformation, we can easily get to the Jordan form, that is why we are doing this type of a transformation. And so, now you can see that this is what the matrix will look like, or the transformed state equations will look like. Okay. And now, directly since this will be the transform equation, we know what the solution will look like, because here we have a 2 cross 2 Jordan block. So, corresponding to that Jordan block, the exponent will look something like this, and for the 2 part you will have e to the power of 2 t. Now, the only thing that I do not know is z1, z2, z3 0, but I know the relationship between x and z. So, from there I can find out z1, z2, z3 0 using this relation, and from here this initial condition was 1 1 1. So, if you take 1 1 1 here, minus 4 minus 2 1 you will get, you plug it in here. So, I am plugging in here, you will get this expression, but this is, so these are the state variables z1, z2 and z3, but I want the answer in terms of x, right. So, I can easily go to x now, because I have the relation between x and z. So, x will be this. So, if you go ahead and calculate, this will be your final solution. Okay. So, this is how you can use our Jordan method to find out the solution, or the Jordan matrix canonical form to find out the solution of the state equation. I will end this lecture here today. Thank you.